Welcome to another deep dive. This time we're exploring the world of modified gravity theories.
Always exciting.
Always. And, full disclosure, the title of the paper we're looking at today, Weak Gravity Limit in Newer General Relativity, already has me feeling a little intimidated.
I uh I can see why, but don't worry, we'll break it down together and hopefully by the end it'll all make sense.
Okay, well, I'm going to hold you to that. So first things first, even IS, Newer GR, it sounds like some kind of futuristic energy drink or something.
Uh-huh. Yeah, I can see the newer GR. It's actually it's one of many attempts to kind of rethink how we describe gravity.
Okay, so we're going beyond Einstein's theory of general relativity.
Exactly. So in Einstein's theory, gravity is all about the curvature of space-time, right?
Yep.
Like massive objects warp the fabric of space-time around them, and that's what causes gravity.
Right, like that classic analogy of a bowling ball on a trampoline.
Yeah, exactly.
Yeah.
But newer GR says, hey, let's try a different approach. Instead of curvature, it uses this concept called nonmetricity.
Nonmetricity. Okay, now you're just making up words.
Uh-huh. Fair enough. It sounds complicated, but think of it this way. Imagine a world where your measuring stick changes length depending on where you are.
So like at Alice in Wonderland when she drinks the potion and shrinks and grows.
Kinda. But instead of Alice changing size, it's the actual way we measure distances that's changing. That's non-metricity in a nutshell. The way we measure distances is warping, not space itself.
Okay, I think I'm starting to get it. So instead of like the fabric of space-time bending, it's like the ruler itself is getting distorted.
Exactly. And that distortion, that's what newer GR uses to describe gravity.
Wow, okay, my brain just did a somersault. So how does this non-metricity thing actually work in practice? Like, are there still equations and stuff?
Absolutely. It's still a mathematical theory,
Mm.
but the math gets pretty intense.
I bet. So how do they actually use this non-metricity to describe how gravity works?
Well, the key is that newer GR relies on this concept of a flat connection in spacetime. It's kind of like imagining a cosmic grid underlying everything.
A cosmic grid, so like a giant graph paper for the universe.
You got it. And the specifics of how gravity messes with this grid are controlled by 5 parameters. Think of them like knobs you can tweak.
5 knobs, huh? Sounds like we could get some pretty wild variations of gravity depending on how we adjust those.
That's exactly what makes it so interesting. By adjusting these 5 parameters, you can get a whole range of different flavors of newer GR. And that's where the weak gravity limit comes in.
Right, the weak gravity limit. So remind me again, why is that so important? Why are we focusing on that aspect of newer GR?
Well, it's all about testing these new gravity models in a regime where we already have a lot of data from general relativity. Remember, general relativity works really well in most situations, especially where gravity is relatively weak.
Okay, so we're basically using general relativity as a benchmark to see how these new theories stack up.
Exactly. It's like putting them through a basic fitness test. Can they reproduce the results we see in everyday situations where gravity is relatively weak?
Right, makes sense.
Oh,
So if
yeah.
a new theory can't even handle the basics, it's probably not going to be a contender.
Precisely. And one of the key tests is looking at how these modified gravity theories affect different types of gravitational waves. Those ripples in space-time we've actually detected.
Oh, right, gravitational waves.
Yeah.
Yeah, those are like the rock stars of astrophysics these days. So what did they find? Does newer GR make those waves do anything weird?
It does in some cases. Remember those 5 knobs we talked about? Depending on how you tweak them, newer GR can make those gravitational waves do some pretty crazy things.
Oh, that doesn't sound promising. You need an example. What kind of crazy things are we talking about?
Well, for example, one of the parameters, A1, controls the behavior of tensor waves, which are the type we've actually observed. If you set A1 to 0, those tensor waves essentially vanish. Poof, gone.
Wait, are you serious? The gravitational waves, those ripples in spacetime, they could just disappear?
In this particular version of newer GR, with A1 set to 0, yes. It highlights how sensitive these modified gravity theories are to even small changes in those parameters. And it gets even weirder when we start looking at the other types of gravitational waves, the vector and scalar waves.
Okay, I am officially intrigued. What happens to those waves in newer GR? Do they also vanish? Or do they do something even crazier?
Well, each type has its own unique quirks. Let's start with the vector waves. They're kind of tricky because they have this thing called gauge freedom.
Gauge freedom. Okay, now I'm really lost.
Think of it like having some wiggle room in how you describe them mathematically. It's like you can choose different coordinate systems to describe the same physical phenomenon.
Okay, I kind of get that. So it's not that the vector waves themselves are changing, but the way we're describing them might have some flexibility.
You got it.
Yeah.
But that flexibility isn't unlimited. There are still some rules they have to follow, some constraints that keep them from going completely haywire.
So it's like they have a bit of freedom to move around, but they're still bound by certain limits.
That's a great way to put it. And depending on the values of those 5 parameters, those knobs we can tweak, those vector waves can be completely tamed or let loose, running wild and causing all sorts of chaos.
Okay, so we've got disappearing tensor waves and rebellious vector waves. What about the last type, the scalar waves? What do they do in newer GR?
The scalar waves. Now, this is where things get really interesting and potentially disastrous.
Oh, that doesn't sound good. What's the problem with the scalar waves?
It turns out that trying to make the scalar waves behave nicely in newer GR leads to a big problem, something called ghosts.
Hold on, ghosts, like actual spooky ghosts haunting the equations.
Not literally, of course.
Yeah.
But in theoretical physics, ghosts are these mathematical artifacts that pop up in some theories, and they can cause all sorts of trouble.
Okay, so these theoretical ghosts, they're not like Casper the Friendly Ghost. They're more like the poltergeists of physics, right?
You could say that. They're basically these instabilities in the theory that can make the whole thing fall apart.
Yikes. That doesn't sound good at all. So does that mean newer GR is a bust? Is it back to the drawing board for these physicists?
Not necessarily. While this ghost problem is a major challenge, it doesn't completely rule out newer GR.
Okay, so there's still hope.
There might be. The authors of this paper dug deeper and found some intriguing cases where newer GR behaves surprisingly well, at least in the weak gravity limit. It's like finding a hidden door in a haunted mansion that leads you right back to the familiar world outside.
So newer GR can pretend to be regular GR, at least sometimes.
In a way, yes. They found a specific combination of parameters where newer GR starts to look a lot like standard general relativity, at least when gravity is weak.
Okay, that's pretty interesting. But if it's just copying GR, what's the point of even having newer GR in the first place?
That's a great question. And it leads us to one of the most fascinating aspects of this whole thing. It turns out that this GR mimicking version of newer GR has some hidden depths. It connects to another modified gravity model called unimodular gravity.
Unimodular gravity, another theory. My head is spinning.
I know, right? But stick with me. This is where things get really exciting.
All right, I'm ready. Hit me with it. What's unimodular gravity all about, and how does it connect to newer GR?
Well, unimodular gravity is a fascinating beast in its own right. But we'll save that for next time.
Ooh, a cliffhanger. All right, I guess I'll have to tune in for the next part to hear about this unimodular gravity thing. I'm already hooked.
Great. I'm looking forward to diving into it with you.
All right, so we're back and ready to tackle this unimodular gravity thing.
Excellent. I'm excited to dive in.
Me too, but before we go too far, can you remind me what exactly unimodular gravity is again?
Sure. So, unimodular gravity, it's this idea that the volume of space-time can't change. It's like saying, hey, space-time, you can warp and bend all you want, but your total volume has got to stay the same.
Okay, I vaguely remember that from last time. But how does that tie in with newer GR, especially this version that seems to mimic regular old general relativity?
Right. That's the key connection. Remember those 5 parameters we talked about? Those knobs we can tweak in newer GR? Well, the authors found that when they set those parameters to a very specific combination, newer GR starts behaving just like unimodular gravity, at least when gravity is weak.
So it's like they found a hidden tunnel connecting these two seemingly different theories.
Exactly. And this tunnel, this connection, it's particularly intriguing because unimodular gravity, well, it has a history of being proposed as a potential solution to some of the problems that plague general relativity.
Problems like what?
Well, one of the big ones is the need for dark energy to explain the accelerating expansion of the universe. You see, general relativity works incredibly well for most things, but when we try to explain why the expansion of the universe is speeding up, we have to introduce this mysterious dark energy that makes up, get this, like 70% of the universe's total energy.
Dark energy, right. That invisible stuff that's pushing everything apart. It's always seemed a bit like a fudge factor to me, like physicists just made it up to make the equations work.
Well, a lot of physicists feel the same way, and that's where unimodular gravity comes in. Some physicists think that by constraining the volume of space-time, unimodular gravity might be able to explain that accelerated expansion without needing to invoke this mysterious dark energy.
Whoa, hold on. Are you saying that unimodular gravity could potentially get rid of dark energy altogether?
It's a possibility, though a hotly debated one. The idea is that by restricting how space-time can change its volume, you're essentially introducing a new mechanism, a new driving force for the universe's expansion.
Okay, my mind is officially blown. So, by finding this link between newer GR and unimodular gravity, does that lend more support to the idea that unimodular gravity might be the real deal?
It's definitely a tantalizing connection. But hold your horses. It's not all sunshine and roses.
Oh, what's the catch?
Well, remember those pesky ghosts we talked about earlier, those instabilities that can plague these modified gravity theories?
Oh no, not the ghosts again. Can't we ever escape those spooky troublemakers?
It seems not. And unimodular gravity, well, it turns out it has its own share of ghostly issues too. In this case, the ghosts, they seem to pop up because of the restrictions that unimodular gravity places on space-time's volume.
So it's like trying to stuff too much furniture into a tiny room. You're bound to break something.
That's a great analogy. And when it comes to unimodular gravity, those broken things are these ghostly instabilities that can make the theory go haywire.
Okay, so unimodular newer GR, it might have some ghostly problems, but does that mean the whole theory is doomed? Is it back to the drawing board?
Not necessarily. The authors of this paper, they dove deep into the math and they found that these ghostly issues, they might only show up in very specific situations like when gravity is super strong, near black holes or something.
Well, it's like those ghosts are only active in certain parts of the house, and we just need to figure out how to avoid those rooms.
Exactly. And remember, we're mostly concerned with the weak gravity limit, the regime, where we can test these theories against what we already know from general relativity.
Mm.
And in that regime, well, those ghosts might not cause too much trouble.
Okay, that's a bit reassuring. So, besides those potential ghosts, what else does this connection to unimodular gravity tell us about newer GR?
Well, it opens up a whole Pandora's box of questions. For one thing, unimodular gravity has this peculiar feature. It has more degrees of freedom compared to general relativity.
Degrees of freedom. Refresh my memory. What are those again?
Think of them as the different ways a system can wiggle and jiggle general relativity. It allows for a certain number of these wiggles. But unimodular gravity, it throws in some extra ones.
So it's like unimodular gravity is a more flexible dancer, able to bust some moves that general relativity just can't handle.
Uh-huh. I love that analogy. And those extra moves, those extra degrees of freedom, they could have some pretty mind-blowing consequences for how gravity behaves, especially in extreme environments like black holes or the early universe.
Okay, this is getting really interesting. So, more degrees of freedom, that's one of the things that sets unimodular gravity apart. Anything else?
Oh, there's more. And this is where things get really weird. Get this, the authors found that this unimodular version of newer GR actually has even more degrees of freedom than previously thought.
Yeah.
And get this, it's a fractional number.
A fractional number? How is that even possible? That's like saying you have half a cat.
I know, it sounds crazy, right? But in the wacky world of theoretical physics, sometimes things get a little fuzzy.
Fuzzy is right. So, what does it mean to have a fractional degree of freedom? And what does it tell us about newer GR?
Well, that's a question that's still keeping physicists up at night. It's a deep and subtle issue that touches on some really fundamental questions about how we understand and describe physical theories. But the bottom line is that this discovery of fractional degrees of freedom in unimodular newer GR, it highlights just how much we still don't know about gravity and how it works.
This is all so mind-blowing. It's like we stumbled onto a whole new continent of physics, and we're just beginning to explore its uncharted territories.
That's a fantastic way to put it. And who knows what amazing discoveries await us as we venture further into this strange and exciting new world.
Well, before we get too lost in the theoretical wilderness, I think we need to take a step back and try to make sense of all this. We've explored the nuts and bolts of newer GR, encountered those pesky theoretical ghosts, and uncovered this surprising connection to unimodular gravity. But what does it all mean?
That's the big question, isn't it? And that's exactly what we're going to tackle in the next part of our deep dive. We'll zoom out, look at the bigger picture, and explore what these findings might tell us about gravity and the universe itself.
All right, I'm ready to connect all these dots and see what kind of cosmic masterpiece emerges. Lead the way.
All right, so we've journeyed through the strange world of newer GR.
Yeah, we've seen some pretty wild stuff.
We have nonmetricity, ghosts, fractional degrees of freedom. My head is still spinning. It's a lot to take in,
Yeah.
but it's all about pushing the boundaries of what we know about gravity.
Exactly. But okay, big picture time. Why should we even care about newer GR? What's the point of all this theoretical gymnastics?
That's the key question, isn't it? At
Yeah.
the end of the day, newer GR is all about trying to solve some of the biggest mysteries in cosmology.
Yeah.
Mysteries that our current theory of gravity, Einstein's general relativity, well, it struggles to explain.
Okay, so like what kind of mysteries?
Well, the big one, the elephant in the room, is the accelerated expansion of the universe.
Yeah, I remember learning about that. It's like the universe is not just expanding, but it's expanding faster and faster.
Right. And to explain that within the framework of general relativity, we need to introduce this mysterious thing called dark energy.
Dark energy, right? That invisible force that's pushing everything apart. It always seemed kind of, I don't know, made up to me.
Well, a lot of physicists feel the same way.
Yeah.
It's this unknown entity that makes up like 70% of the universe's energy budget, but we have no idea what it is.
Yeah. So is Newer GR saying, hey, maybe we don't need dark energy after all?
It's a possibility.
Hmm.
That's one of the things that makes it so exciting. With newer GR, by adjusting those 5 parameters, we might be able to find a way to explain the accelerated expansion without needing to resort to this mysterious dark energy.
Wow, okay, I'm starting to see why physicists are so intrigued by this, but let's be real here. How likely is it that Newer GR is actually the right way to understand gravity? We've seen it has its own problems, like those pesky ghosts.
True, newer GR is still a work in progress, and it definitely has its challenges. Those ghosts are a big concern, and there are other theoretical hurdles to overcome.
So it's like Newer GR is a promising young athlete, but they're still prone to tripping over their own feet.
Haha, yeah, that's a good way to put it.
Huh.
But, even if newer GR doesn't end up being the ultimate theory of gravity, the process of exploring it is still incredibly valuable
How?
because it forces us to think outside the box, to question our assumptions about how gravity works. It's like a mental workout for physicists, pushing them to come up with new ideas and explore uncharted territory.
So even if they don't win the gold medal, they're still getting stronger and more flexible in the process.
Exactly. And who knows, maybe the insights we gain from studying newer GR will lead us to an even better theory down the line.
I love that. It's like saying, hey, even if this particular path doesn't lead us to the treasure, we're still discovering new landscapes and learning valuable lessons along the way.
Absolutely. And that's the beauty of science, right? It's all about exploration, curiosity, and the willingness to venture into the unknown.
Well, I have to say, this deep dive into Newer GR has definitely been an adventure. I feel like I've learned so much and expanded my cosmic
Me
horizons.
too. We've
Yeah.
gone from the basics of nonmetricity to the weirdness of ghosts and fractional degrees of freedom. It's been a wild ride.
And who knows, maybe one day those wild ideas will turn into concrete discoveries that revolutionize our understanding of the universe.
I have no doubt that exciting new discoveries are waiting just around the corner, just waiting for us to uncover them.
Well said. And on that note, I think it's time to wrap up this deep dive into Newer GR. Thanks for joining us on this cosmic journey.
It's been a pleasure exploring these mind-bending ideas with you. And remember, the universe is full of mysteries, and the quest to understand them is what makes science so thrilling. So keep those minds curious and never stop exploring.